So, welcome to the second unit in IB Chemistry for this year, Stoichiometric relationships. And in this lesson, we're looking at the particulate nature of matter and chemical change, which hopefully should be a review for most of you about what you've done in IGCSE. So again, it'll have learning objectives, things that you have to understand and what you should be able to do. I'll let you look at that at your own leisure and tick off when you meet these learning objectives. So touching on some of the nature of science, we'll first look at the differences between a law and a theory. Okay, so they are both developed from experimental data, but they both also have exceptions to the rule, and they both can be modified or they can be both rejected. Okay, so a theory is an explanation that provides an understanding across a range of phenomena and disciplines. Okay, so the theory of gravity is an explanation of why I am stuck to the earth and not floating around in space. And a law is a description of regular patterns of behavior. So the law of gravity says, well, basically, because we're all sticking to the ground due to gravity, then that is a regular pattern of things on Earth, so it is a law of gravity. Okay, so in terms of stoichiometry, we have the law of definite proportions. So a compound always contains the same proportion of elements by mass. Okay, so if you have a compound of sugar, it's going to have the same proportion of carbon, hydrogen, and oxygen. And this was developed by Joseph Louis Proust, a French chemist, and he showed experimentally that both artificial and natural copper carbonate have the same proportion of the elements of copper, carbon, and oxygen. Okay, so what's that basically saying? Well, it's saying that copper carbonate, whether you make it by experiment or whether you find it on the ground, by definition, a molecule or a compound of copper carbonate will have the same proportion of copper, carbon, and oxygen. But what about this compound? So there was another Swedish chemist named Berzelius who disagreed completely with Proust. Okay, so he said that non-stoichiometric compounds, for example, plastics like polymers or polymers like plastics, as well as isotopes, are an exception to the rule. For example, iron oxide is usually found as iron 0.84 oxygen because you've got iron 2 plus ions and iron 3 plus ions. So in comparing the two theories, one of Proust and one of Berzelius, we can also invoke something known as the principle of Occam's razor. Okay, so William, he was from Occam, and he was English and a monk, and he was a middle century monk, and he basically said that a theory should be as simple as possible while being able to maximize how well the theory can explain things. Okay, so it's basically keeping it simple. You shave away the unnecessary parts of the theory. So with that in mind, maybe just think about, why do you think that Proust won over Berzelius in terms of the scientific theory of what a compound is? So hopefully your brain has been successfully stretched by that little conundrum, which hopefully has been solved by Occam's razor. So when looking at stoichiometry, we have to have certain terms that we must use in our answers, and so we can all have a common language so we can understand things. So many of them are familiar. So an element is of course a substance composed of atoms having identical numbers of protons in each nucleus. Okay, so an element of carbon will always have 6 protons in its nucleus. That's what makes it carbon by definition. An atom is the smallest part of an element, at least in chemistry. I'm not going into quantum physics here. And a compound is 2 or more elements that are chemically bonded together. So carbon dioxide is a compound of carbon dioxide because you have 2 elements, carbon and oxygen, bonded chemically together. And we also have mixtures, and mixtures contain 1 or more element or a compound that are not chemically bonded together and so retain their different individual properties. Okay, so carbon sulfide, for example, or copper sulfide, together they can react to form copper sulfide, but as a mixture, copper will behave as a metal and sulfur will behave as sulfur does. And there's two types of mixtures. There's homogeneous, having uniform properties, of course, from the homo start, so meaning the same. And then you've got heterogeneous mixtures, which are hetero, so they have non-uniform properties, and hetero means different. Okay, so matter can be broken down into two different things, into pure substances, where your elements and your compounds, and to mixtures, which we've just discussed can both be homogeneous or heterogeneous. Those elements can be further broken down into atoms, which are individual atoms, or molecules, where you have the two of the same atoms bonded together, like in oxygen. Compounds can be either defined as molecules or ions. Okay, so molecules are like water, where the compounds are chemically bonded through covalent bonding. In the example of water, H bonded covalently to oxygen, or ions, where you've got sodium chloride, for example, where it's an electrostatic interaction, it's more ionic bonding. Sodium ion is electrostatically attracted to the chloride anions, in a giant lattice. And compounds can be broken down into elements through chemical processes, whereas mixtures can be formed into pure substances by physical processes. And again, terminology. So you've got three states, which we've extended on in IGCSE to a fourth state, aqueous, with aqueous meaning dissolved in water. Okay, so a bit of Latin for you, aqua, water. Okay, so that means just dissolved in water. And chemical formulas always have subscripts, which is the number of atoms in a molecule, and also chemical symbols, and a coefficient, meaning how many you've got. Okay, so 2H2O means you have 2 water molecules. So hopefully you're all familiar from previous years in chemistry, please. And we also have the states of matter. Okay, so there's 3 states of matter: solid, liquid, and gas. Again, this is kind of revising over your GCSE, but you've got solids, which have a fixed volume and a fixed shape. They cannot be compressed, unlike gases and to a lesser extent liquids. And the attractive forces between the particles hold the particles together in a close, packed arrangement. Important to note that particles indeed vibrate, but they vibrate in a fixed position. Okay, liquids also have a fixed volume, but they can take the shape of the container. Some could argue cats are liquids, but still they have no fixed shape and cannot be compressed. Okay, forces between the particles are weaker than the solids, and particles vibrate and rotate and translate. They can move around a lot more. They have a lot more degrees of freedom than a solid. And gases, the only one with no fixed volume and no fixed shape, they can also be compressed. Okay, and forces between the particles is taken as 0. We'll just say that they're theoretically at infinite distance, and the particles can vibrate, rotate, and translate faster than in a liquid because the molecules are widely separated. Okay, so we've also got the changes of state. So this is the solid, of course, because the particles are all quite closely bound together and vibrating on the spot. We've got liquids, which have a bit more degrees of freedom, and then we have the gases, which have the ultimate degrees of freedom, so widely separated apart. Okay, so you've got solid going into liquid is melting, liquid going back into solid is freezing, and liquid going to gas is vaporization, and the gas going back into liquid is condensation. And the final two are solid going into a gas is sublimation, so carbon dioxide, for example, does that as a compound, and gases going back into solids is known as deposition, which you sometimes see when you're using paint guns, if the temperature is hot enough. Okay, so the heating curves, which you should also be familiar with from GCSE, remembering of course that the Systems International unit for temperature is the Kelvin, which is degrees Celsius plus 273.15. I'll just add that there. And what happens is that the flat line on a heating curve illustrates the substance is pure. Okay, so if this was water, it would be boiling at 100 degrees Celsius, for example. And energy added at a phase change goes into breaking the interparticle forces, not raising the temperature. Okay, so at this temperature here, okay, what's happening is that there's phase change happening, and what you're doing is breaking the intermolecular bonds and not increasing temperature. That's why it's going flat at the phase change. So there's just an example here of a generic substance. The melting point is between the solid and liquid interface, and the boiling point at the liquid and gas interface. And you can see what's happening in terms of phase changing and the different names of those phase changes from the animation at the bottom of the page. So let's now look at the law of multiple proportions from English chemist from the 19th century, John Dalton. If two elements form more than one compound between them, then the ratios of the masses of the second element, which combine with a fixed mass of the first element, will be ratios of small whole numbers. Okay, so basically it's saying that elements combine to form compounds in whole numbers. You don't get compounds of C half O 3/4. Okay, it's carbon CO 1:1 or CO2 1:2. This is a slight improvement on Proust's law, which we looked at previously, and also Lavoisier's conservation of mass. And these three laws then form the basis of chemical formulae, names, and the topic of this next unit, stoichiometry. So here's some examples of experimental evidence of stoichiometry. So you can clearly see that the ratios between the oxygen and nitrogen in the nitrous oxides are whole numbers, 2:1, 1:1, 1:2, and 1:4. Okay, looking at the ratios, so the smallest ratios are illustrated there. And this kind of proves that compounds form whole number ratios. In terms of polyatomic ions, these are ions with atoms which are positive, which we call cations, or negative, anions, and polyatomic ions are covalent molecules. Okay, so there's covalent bonding between the atoms in that polyatomic ion, but they have a charge which acts as a unit for ionic compounds. And these must be memorized. Okay, the list is on the next slide, and you will learn how to work these out hopefully soon. Okay, so these are the polyatomic ions that you should really have memorized from GCSE. Okay, so sadly they're not in your data book, so you're going to have to memorize them. And also shows where they've actually derived from. So sulfates are formed when sulfuric acid forms salts, for example. So naming covalent compounds. Okay, so covalent compounds are formed by the sharing of electrons. Again, you should have known that from last year. So to name these compounds, you must add prefixes to show how many atoms are in the formula. And you know it's covalent because there's a non-metal combined with a non-metal. If it was a metal with a non-metal, then that would look more than likely to be ionic. Okay, so add prefixes to all atoms but omit mono for the first element, and add ide for the last element. So the example I've given here is carbon monoxide, CO. It's carbon and oxygen, so it's not monocarbon monoxide. We just don't bother with that. We just say it's carbon, and just so you can tell that it is only one oxygen, it's called monooxide, and therefore dioxide is CO2. So how do we name ionic compounds? Ionic compounds are formed from the attraction of positive ions or cations and negative anions. So to name these compounds, find the charges and balance the charges. You know it is ionic because there's going to be a metal combined with a non-metal. So for example, copper chloride, copper is a metal, chlorine is a non-metal, so it's going to form an ionic compound. The cation always comes first, the anion second, and you usually put ide at the end of the anion. And the charges balance. Okay, so the next thing is balancing equations. So here we have the reaction of a hydrocarbon with oxygen being combusted to form carbon dioxide and water. Okay, so the first thing you do is make a table to list out the elements on the left and the right hand side. Okay, so we have on the left hand side 6 hydrogens, 6 carbons, 14 hydrogens, and 2 oxygens. Here we have 1 carbon, 2 oxygens, and 2 hydrogens, oh, and another oxygen there, making 3 in total. Okay, so that's the first thing you do. So the next thing you have to do is begin with the most complicated compound and balance the equation for this. Okay, so we need 6 carbons on the left hand side, so if we multiply CO2 by 6, okay, we then make another row in the table and basically multiply the carbons by 6 and oxygens by 6 as well, so you get 12 for carbon dioxide in terms of oxygens plus the 1 that we've got for water. Okay, so that's the first part of the equation there. So now balance out the number of carbons on the left and right hand side. The next step is to balance out the number of hydrogens. Okay, so we have 14 hydrogens on the left side. We need to have 14 hydrogens on the right side, so we multiply the water by 7. Okay, 7 times 2 being 14. So now we add another row to the table. So we have now on the right hand side after this calculation 6 carbons, 14 hydrogens and 19 oxygens. So they don't quite balance out yet. So to balance the equation completely, we need to be able to balance out the least complicated compound, which is going to be here, oxygen. So we need to multiply it by 19 over 2 to get 19 oxygens, and that's the balanced equation. Ideally, you would use whole numbers, so you multiply everything out by 2 to get a complete balanced equation, which is the next slide. I've jumped again. Okay, and double check to ensure it's balanced and the numbers are of the lowest common factor.